Hi everyone. Trying out a new screen recorder here, so hopefully that's a little bit more stable and I'll get less corrupted videos. But this is just a continuation of part one. So I think the last thing I talked about was that you need to keep this order. If you're going to do the product rule for two matrices, you need to always have A first and then B, since order matters when you're multiplying two matrices. The next thing I wanted to talk about was finding the determinant of a matrix. So I'll start with the 2 by 2 one. Hopefully you remember from linear algebra, this is just going to be this times this minus this times this. One thing I wanted to point out is that I'm not always going to write DET when I want to talk about the determinant. Another notation for that is just these two vertical lines there, but it's the product of these two minus the product of these two. Taking the determinant of a 3 by 3 is a little bit more involved. So let's say that we've got this other matrix Z that's a 3 by 3. The way that I like to think about this is to do it by row. So I've got sort of my Z11, Z12, and Z13 on my top row there. And the way that I'll set it up is we're going to have, determinants. We're going to have three determinants, but what we multiply them by is Z11 goes here, Z12 goes here, Z13 goes here, and the signs of these, so whether it's positive or negative, are going to alternate in between. So we have positive, negative, and positive. The thing that we're going to multiply each of these by is the determinant that's left over when you get rid of the row and the column. So I'll start with this first one here. If I want to talk about Z11, if I cross out the first row and the first column, because that's where it is, then what I'm left with is this matrix here that's a 2 by 2. So these entries here are what I'm going to multiply whatever's in the Z11 spot by. So I'll say it's those four objects. Next one, Z12, means that we're going to look at the remaining ones. So that's going to be these two and these two, so it's sort of split up. Across those two columns. And then the last one will just be what remains when we get rid of the third column, first row. So that'll be the determinant of all this stuff left over. This is probably a little crazy to look at, right, with all the colors on here, but again, this should just be a reminder from linear algebra. There's plenty of resources to see examples of determinants for 3 by 3s. Next question I want to talk about is can we invert a matrix? And so the inverse of a matrix is kind of what we need to do rather than dividing by a matrix, since we can't just have one matrix divided by the other and divide all the individual elements. We can't do that. So we need to have some way to invert a matrix. And the way we do that is with this a to the -1 notation here. So the way that we take care of an inverse of a matrix is we take these two entries and switch them between one and the other. And then these two entries in these corners stay exactly where they are, but they become negative. It's 1 over the determinant of the original matrix multiplied by all that. So that's another use for the determinant. Just put another way, if you are used to this A, B, C, D form, A and D switch places, B and C become negative. And that's our inverse matrix. A question that you should ask yourself is whether or not we can invert a matrix. That's useful in some theory examples here. So the inverse of the matrix exists if and only if this determinant is not 0. Since if the determinant of A, if that number was 0, then we'd be dividing by 0. So that answers the question. When is a matrix invertible? Well, that's when the determinant of A is not equal to 0. A big skill that you'll be using in almost every one of these problems in Chapter 4 is this reduced row echelon form, or Gaussian elimination. You might recognize this as an augmented matrix, but if I give you some 2x2 matrix that looks like this, then you should be able to, again, most of the time our goal is to find the identity matrix, and that'll tell us what our x and y components are, whatever we use to define these two columns here. So I'll show plenty of examples of that, but my assumption is that I'm not going to explain exactly what I'm doing every time, so there's not going to be a lot of this row minus that row or 3 times this. I'll just assume you can follow the steps that I'm doing. So I'll do the problems at speed when I start doing Gaussian elimination, but that's a good skill to have. The last little piece that I want to talk about, and this will be useful for some of the theory and getting our equations down, is to understand. I'm going to use a different variable here. Understand what's going on here. So A is going to be some matrix. This x vector here is a vector since it's got the arrow. And lambda is a constant, or what we call a scalar. So it's just one number, 1 by 1, and then we have the vector again. So if you first look at this and take sort of a naive view, you might say something like, well, A is equal to lambda, right? But we can't do that, and the reason for that is that this is a matrix and this is a scalar. And if we say that they're equal to each other, that means they're the same thing. So they're not quite the same thing. They're similar to each other. A and lambda are similar to each other, but that's the goal of finding this eigenvalue here. Is there some value that if we set up this equation that we end up with the same thing? Here, let's see, this is going to be a matrix is a 2 by 2, right? This column is a 2 by 1, so this should be a 2 by 1. This is a 1 by 1, essentially, and then this is a 2 by 1. So when we multiply some scalar, let's say 7 times a 2 by 1, in both cases we're going to get a 2 by 1. I shouldn't call this a 1 by 1, that's maybe bad notation. But the idea is on both sides of this equation we're going to end up with a vector, a 2 by 1. Okay, so if we do a little bit of algebra with this, we can subtract the lambda times x to both sides. What's going to result from that is a vector. All right, since I said this is a 2 by 1, so we want to put 0 and this on there. And then we can separate, combine like terms, so we multiply both of these by the vector x. The thing with this is, let's say that we tried to take this matrix, I'm going to call it 1, 2, 3, 4, for an example here, and I'm going to say lambda is equal to 2. So if you're not familiar with taking a matrix and subtracting a scalar from it, you might first think that you need to just subtract 2 from every single one of these, right? So minus 2, minus 2, minus 2, but that's not quite right. What you actually want to do here, in order to write this scalar 2 as an equivalent matrix, or as a similar matrix, is to multiply it by the identity matrix. So the identity matrix is this matrix that looks like this. And so the result of that would be this down here, which is 2002. So you can see what that might look like down here, but yes, matrix, scalar, we need to make sure that these are both matrices. So 1, 2, 3, 4 minus 2002, that'll give us this matrix here. Okay, that's going to be it for this video, and I'll be making, I see that the next video for linear algebra review got corrupted as well, so I'm going to be making part 4 right now. Okay, see you then.